Hello, dear viewers. Greetings to everyone watching us online. We continue our series of discussions dedicated to the American space tricks. Let's recall the following. Even before perhaps the most spectacular act of Soviet-American cooperation in space, the Apollo-Soyuz project, the Soviet Union had established international contacts with France, which were implemented in hardware and in actual space missions. Thus, the Encyclopedia of Soviet Cosmonautics, a beautifully published 1981 edition, states that an agreement on cooperation between the USSR and the French Republic was signed in 1966 during the visit of French President Charles de Gaulle. On the slide now on the screen, you can see the areas of research that were planned within the framework of this agreement. The encyclopedia notes that the most interesting result of this collaboration was the experiments carried out with Lunokhod 1 and Lunokhod 2. It also features photographs of spacecraft that were built and launched as part of the cooperation between Soviet and French engineers. At the same time, in 1985, another encyclopedia titled Cosmonautics, which we've already mentioned several times in this studio, included a short note in the section devoted to the Luna spacecraft series. It said that Luna 17 was launched on November 10, 1970, and showed a diagram of the lunar lander carrying the Lunokhod. And, in fact, that was where the entire account of this fascinating event ended. Meanwhile, in 1971, issue number 6 of the Bulletin of the Academy of Sciences of the USSR published an article on the Soviet-French experiment in lunar laser ranging. That was just half a year after Luna 17 traveled from Earth to the Moon. In that article, the authors Kokorin and Vedeshin in 6 pages described what took place, what experiments were carried out, and what their scientific value was. The paper outlined the idea of conducting a joint Soviet-French experiment using laser retroreflectors. This idea was first proposed in 1967, just a year after the signing of the General Cooperation Agreement mentioned earlier. After studying the technical possibilities, specialists from the USSR and France agreed to work on laser ranging of retroreflectors installed on the Moon's surface. The French side assumed responsibility for manufacturing the panel of laser retroreflectors, while the Soviet side was to deliver them aboard a lunar probe. In other words, the responsibilities were divided. The retroreflectors were made by the French, and delivered to the Moon by the Soviets. On the slide, you can see a photograph of that very French retroreflector. The Soviet unmanned lunar probes, Luna 17 and Luna 21, were launched in 1970 and 1973 respectively, delivering Lunokhod 1 and Lunokhod 2 to the Moon. The landers, or rather, their museum replicas, are shown on the slide. How did all this work? To determine the distance to the Moon, laser beams were sent from Earth. It turned out that the Moon is gradually moving away from Earth, by about 38 millimeters per year. The beams were aimed at Lunokhod 1. The reflected photons were captured, and the time spent on the round trip was recorded. Knowing the speed, which is constant, scientists could calculate the distance with the required precision. On the slide, you can see an image showing where that French retroreflector was mounted on Lunokhod. The overall setup looks about as simple as something from a 6th grade physics textbook. The beam hits, reflects, and returns to Earth. A seemingly basic physical principle, but at that time already perfected in engineering, allowing researchers, as reported in the results, to measure the Earth-Moon distance with an accuracy of 40 centimeters. It was specifically noted that a French retroreflector was installed on our rover. That's why, The first experiments using it were conducted in 1971 in both the USSR and France. So, there's no doubt that Lunokhod 1 really was on the moon. However, at some point, it suddenly stopped reflecting laser beams, as if it had disappeared from its spot or sunk somewhere. Such terms were even used at the time. In short, Lunokhod vanished, or at least it seemed that way from Earth, and this situation lasted for a full 37 years. The 1971 article in issue number 6 of the Bulletin of the Academy of Sciences of the USSR included the technical parameters of the measurement accuracy, which you can now see on the slide. Data from Lunokhod were received by laser ranging equipment, specifically by a 2.6-meter telescope installed at the Crimean Astrophysical Observatory of the USSR Academy of Sciences. The photo you see now is taken directly from that scientific paper. In fact, until 2010, scientists supposedly did not know the exact location of Lunokhod 1. At least, that's what foreign specialists claimed. Our researchers, however, insist they always knew its position fairly precisely. Only in 2010, almost 40 years later, did the Americans detect the spot they believed to be the Lunokhod 1 site. They discovered it through photographs taken by their lunar orbiter. The identification was confirmed by control laser firing. The reflected signals matched, confirming the location. By the way, you can now see a photo from Lunokhod 1. The Luna 17 lander that delivered it, and the tracks left by Lunokhod's wheels around it. A little later, about a year afterward, which is quite recent by historical space standards, Canadian researcher Phil Stuke announced to the English-speaking scientific community that he had spotted our Lunokhod 2 in orbital photos of the Moon. Foreign specialists slightly teased him about it, saying that his job was easier than that of his colleagues from the previous 37 years, since the twin brother of Lunokhod 1 had never gone missing and had remained in the Sea of Serenity after landing, with its retroreflectors still functioning. This is what this beauty looks like, a copy of which is now on display in one of the museum exhibits. It's located on the Moon, and it's equipped with various instruments, including retroreflectors whose signals are being received by the Americans. At the same time, the Americans claim that they receive signals from the retroreflectors delivered there as part of the Apollo 11, 14, and 15 missions. Using 5 sources of reflected laser beams, they perform comparative calculations and include the results in their scientific publications. I'm showing this slide specifically to demonstrate that, starting from 2010, Lunokhod 1 and Lunokhod 2 have been used by them as sources of scientific data. It so happens that if you search for laser ranging of Lunokhods in a search engine, you'll find a fairly recent scientific paper from 2023, published in the journal Cosmic Research, Volume 61, Issue 3, on pages 258 to 264. It's titled, On the Laser Ranging of Lunokhods. The author is Nasennik. This paper provides a general description of the arrangement of retroreflectors on the Lunokhods, the basic formulas used for calculations, and some conclusions. The author of this paper is with us in the studio today, our guest from Novosibirsk, Vitaly Nasennik. Hello, I know you have a lot to share with our viewers. The floor is yours.
Hello, Roman. Hello, dear viewers. Let's begin our presentation. To start with, I have 2 video clips that I really like and would like to show you. These are excerpts from the Big Bang Theory and Mythbusters.
To fire laser at the moon. Make it so. There it is. There's the spike.
2.5 seconds for the light to return. That's the moon. We hit the moon.
That's your big experiment? All that for a line on the screen?
Yeah, but think about what this represents. The fact that we can do this is the only way of definitively proving that there are man-made objects on the moon, put there by a member of a species that only 60 years before had just invented the airplane.
What species is that?
I suppose you didn't pick this episode by chance. It's related to lunar research using lasers, right?
Absolutely. I really like showing this scene from the Big Bang Theory because many online commentators have about the same understanding of laser ranging as Penny's boyfriend, Zach.
And what is laser ranging for? Could you briefly explain it to our viewers?
Briefly, it's used by astronomers to refine the parameters of the bodies in the solar system. The bodies in the solar system move along very complex trajectories that depend on their characteristics, primarily mass and shape. Experimentally refining these trajectories allows scientists to determine how much the moon weighs, what its shape is, and to refine the masses of the Earth, Mars, Jupiter, the Sun, basically all the bodies in the solar system. This is important scientific data, and laser ranging is used alongside other astronomical observation methods. One of the most interesting being transits. A transit is when two bodies, for example, a planet of the solar system and some distant, stationary star, align along the same line of sight from Earth. These moments are recorded and also used for refinement. Transits can only determine the angular positions of celestial bodies relative to each other, while lunar laser ranging makes it possible to determine the distance between the Earth and the Moon. It's an additional channel of information that can't be obtained in any other way.
Thank you.
Alright, let's move on. The next episode, this time is from Mythbusters.
So we did the next best thing.
We shined that laser at the moon on the second test, and we got a clear spike back. Photons came back to our receptor. Now, the only way that that could happen is if there was a piece of man-made equipment up on the moon to reflect them back.
So get over it. There's no conspiracy here.
We've been there. We've done that.
Let's try to adopt their model of simple education and conveying very important scientific facts to people in a clear and accessible way. I liked your article and the way you promote it. Please tell us about your conclusions after reading, I suppose, about 250,000 different scientific papers. After you summarized them and came to your own understanding of what was happening back then, about 55 years ago. And also about how that experience could be useful for us, Earthlings, and for Russians as well, in the near future.
I started from the assumption that optics is an exact science, and therefore experimental data must fully correspond to theoretical models. There shouldn't be any errors here, especially in lunar laser ranging. The air doesn't interfere, since there's a vacuum between the moon and Earth. The speed of light is known. It would seem, what could go wrong? What kind of questions could there be? You shine a laser at the moon, get photons back, and rejoice, for there are retroreflectors there, delivered by the Americans and the Soviet Union. Supposedly, that's the conclusive and final proof. And if we believe Leonard, that's the only proof that humans went to the moon.
Let's pause here for a moment and note two possible interpretations of the results of lunar laser ranging experiments. First, they can show whether there's an artificial source of the reflected signal, that is, a retroreflector. And if there is, then we can confidently say that one of the countries delivered it there, right?
Exactly.
And second, knowing the parameters you mentioned, and using complex, or very complex but known formulas, we can calculate with some precision the distance to specific points on the moon.
Exactly. And not only calculate the distance, but also refine the formulas describing the moon's motion, including not just its orbit around the sun and Earth, but also the deformation of the moon itself due to tidal effects from the sun and Earth. There's also the tidal effect on Earth caused by the moon and the sun. A whole range of other factors is considered, down to the movement of Earth's continents. So, with laser ranging, we can measure the precise positions of ranging observatories. And since they're located on continental plates, by comparing their movement over decades, we can measure tectonic plate shifts. This means laser ranging can be used even for such purposes, provided it really is a retroreflector.
Let's try to go over that limitation again. What else could reflect the laser if not a retroreflector?
Let's start with the fact that reflection can come not only from a retroreflector but simply from the lunar surface itself. After all, we can see the moon in the night sky because it reflects sunlight. So, the moon is capable of reflecting some photons, though, of course, it doesn't do that the same way a retroreflector does. The nature of that reflection is quite different. That's why, by studying the statistical characteristics of the received signal reflected from something on the moon, one can try to figure out what exactly it was reflected from. Although that's very difficult to do, because lunar laser ranging experiments are extremely complex. Right now, only 2 countries are actually performing lunar laser ranging: the United States and France. The Soviet Union stopped its lunar laser ranging experiments back in 1984. Since then, Russia still hasn't been able to resume them, even though there have been attempts to start lunar ranging again at the Altai Optical Laser Center. But something just didn't work out. And it's not only Russia struggling with that. For example, Japan tried twice to build a lunar laser ranging station in collaboration with Hitachi and the Tokyo Observatory. Australia also failed to launch a laser ranging system at its Orroral Valley Observatory, even though the equipment had been supplied to them by the United States, already assembled and ready to go. They simply couldn't get it running.
What about the Chinese and the Indians?
The Chinese assembled a setup at the Yunnan observatories. They have one, and I'll talk more about it a bit later. As for the Indians, I've never heard of them doing any lunar laser ranging work. I have no such information. Meanwhile, the simpler task of laser ranging to artificial Earth satellites and orbital debris is much easier. More than 100 laser ranging stations all over the world are engaged in it, across many different countries. But, pardon me, that's for distances of hundreds or thousands of kilometers, while the moon is about 380,000 kilometers away on average, varying from 360 to 405,000.
Does size matter?
Size matters a lot, because the intensity of the reflected signal decreases with the square of the distance. Let's say we move 100 times farther away. If we compare 3,000 kilometers and 300,000 kilometers, the signal level drops by at least 4 orders of magnitude. The pointing accuracy requirements become much stricter. To create a sufficiently bright spot on the moon, you need a very good laser with extremely low beam divergence. That means, first of all, the intrinsic divergence of the laser must be small. Secondly, the larger the diameter of the transmitting telescope's aperture through which the beam is sent, the better, because diffraction causes the beam to spread. If we take a telescope with, say, a 60 centimeter diameter, then due to that size, the divergence will be about 1 arcsecond. At the distance to the moon, that corresponds to a spot about 1.8 kilometers wide. The distance is huge. What seems like a tiny angle becomes significant. Accurately pointing and keeping the telescope locked according to the formulas of Earth-Moon relative motion is a technically challenging task. Japan, in fact, failed precisely at this stage. They had technical issues with telescope control and their guiding system. When it comes to laser ranging of artificial satellites, the task is several orders of magnitude simpler than lunar ranging. This slide shows a very interesting satellite called LIGIOS. There's also its twin, LIGIOS 2, which is simply a brass sphere about 60 centimeters in diameter, covered on all sides with retroreflectors. It just orbits in space at an altitude of about 5,860 kilometers. Its trajectory is known with an accuracy of about 1 centimeter. Using that trajectory, laser ranging stations determine their own locations. You could say it's a kind of geodetic marker.
A calibration tool?
Exactly, a calibration tool whose position is known with extremely high precision, allowing for very accurate geodetic measurements on Earth's surface.
The LIGIOS satellite. Who does it belong to?
There are LIGIOS 1 and LIGIOS 2 satellites. There's also a very interesting Russian satellite that uses a different type of optical element. Not a corner reflector, but a cat's eye retroreflector.
Which country launched those satellites?
LIGIOS was launched by the United States, and the cat's eye satellite was launched by Russia. Here are the retroreflectors. On the left, you can see retroreflector elements in the form of triple prisms. That is, corner-cut cubes, with or without metallization. Notice that the larger element has a metallic coating, while the smaller ones do not. I'll get into more detail about that later. On the right, you see an internal corner of a cube element. These are also made. It uses 3 carefully polished mutually perpendicular mirrors aligned with extremely high precision. Corner reflectors have 2 remarkable properties. First, if a photon enters the corner reflector within its working angular range, no matter from what direction it arrives, it will return back the way it came. With a certain probability, of course, because reflection isn't 100% perfect. Metal-coated corner reflectors have a reflection coefficient of about 0.9, while uncoated quartz prisms have about 0.3, 3 times worse, but they're more stable, because metal and quartz have different thermal expansion coefficients. When the temperature changes, that difference slightly distorts the reflector and affects its reflective properties. Pure quartz elements without metallization don't have that problem. They're more thermally stable and durable. The same applies to the corner reflector. Since it's entirely metallic, there's no conflict between materials, making it quite stable as well. The first laser ranging experiments were carried out by the United States and the Soviet Union almost immediately after the invention of the laser. The idea of using lasers for active astronomy appeared right away. That is, not just observing celestial bodies through a telescope, but sending out laser beams and measuring the time it takes for the reflected photons to return. Back then, ruby lasers with rather long pulse durations were used. During the first experiments, the pulse length was about 1 millisecond, which meant a distance measurement error of roughly 300 kilometers. Later, shorter pulses of about 1 microsecond were used, achieving an accuracy of 180 meters. That was already a scientifically meaningful result. By the standards of the time, it was useful for refining the trajectories of the Earth and the Moon. But gradually the technology improved, and now modern lasers produce pulses lasting tens of picoseconds. In theory, it's possible to measure with millimeter precision, if not for atmospheric interference. At that time, the experiments were conducted by reflecting the beam off the floors of the Flammarion and Albategnius craters. The optical focusing wasn't very good back then. The beams had quite a large divergence, about 10 arcseconds. Modern systems have less than 1 arcsecond of divergence. So, over the past half-century, the technology has advanced a lot. By the way, the Chinese still have quite a large beam divergence, so they've got room to improve.
What's important is that their results aren't zero.
Yes, not zero. How is laser ranging applied? There are certain formulas describing the motion of the Moon and Earth, the deformation of their shapes, and so on. These formulas are quite long, so I didn't include them here. But the point is, if we precisely determine the equations of the Earth's and Moon's motion and send laser pulses while detecting the returning photons, the resulting photons should fall exactly along a straight vertical line. Here, the x-axis represents the deviation time from the calculated value, and the y-axis shows the pulse number. We can see that the reflected photons are located close to the theoretically calculated line, but it's curved, not straight. When it's curved, scientists start thinking and figuring out the reason for the deviation. In particular, they refined the coordinates of their own observatory. When they recalculated the data with those updated coordinates, the pulse alignment improved. This information is provided in the publication Lunokhod 1, Mobile Laboratory on the Moon, Volume 2. It contains quite a detailed description of the experiments carried out at the Crimean Astrophysical Observatory with the retroreflector of Lunokhod 1. However, the problem was stated right away. The registered signal was an order of magnitude weaker than the theoretically expected one. Therefore, the authors doubted the result, assuming the weak signal was due to the laser not being accurately aimed at Lunokhod.
And during what period were these data obtained? And do you remember the approximate year of the paper?
That was 1970. At the time, these were quite fresh results. As soon as Lunokhod was launched, experiments were immediately conducted, and the article was written and published in that book.
So, sometime in the 1970s before 1980?
Before.
All right.
Here are similar data obtained at the American Apache Point Observatory during laser ranging of the retroreflector supposedly delivered by the Apollo 15 mission. The chart is flipped. The time is plotted along the x-axis, and the deviation from the expected time along the y-axis. We can see that at around 45 nanoseconds, the photons cluster into a thick line.
Vitaly Gennadievich, your phrase, supposedly delivered by Apollo 15, adds some intrigue for our viewers. Please continue.
Because down here it says 2,150 photons out of 14,000 pulses.
Is that good, a lot, or not much?
According to their results, they get on average 1 photon per 7 firings. Not 1 photon per firing, 1 photon per 7 firings. It's a very low result, completely unconvincing as evidence that the signal was reflected from a retroreflector.
Please go on.
According to the Apollo fable, there are 5 retroreflectors installed on the Moon. In fact, a 6th one was delivered to the Moon this March aboard the Blue Ghost spacecraft. There's a retroreflector there, but I don't know whether it's being used or not. I haven't yet seen a single scientific publication with data obtained using that reflector, so I can't say anything about it. It's not shown in the picture because I haven't yet seen any scientific data.
Let's clarify once again the descriptive data in the diagram. L1 and L2 are ours. Lunokhod 1 and Lunokhod 2, or more precisely, they're retroreflectors. A11, 14, and 15 are what the Americans claim to be platforms with retroreflectors delivered as part of the missions bearing those names.
That's right. Here are photos of those retroreflectors. These are NASA photographs. Their catalog numbers are indicated. This is the Soviet retroreflector on the Lunokhods. It's half Soviet. The prisms themselves were made in France, while the frame, the lid with its opening mechanism, and all the mounting hardware on the Lunokhod were made in the USSR. So, the prisms are French, but the retroreflector array itself is a Soviet product.
Let's emphasize once more that this image comes from that very article published in the 1971 issue of the Bulletin of the Academy of Sciences.
Exactly.
In that same article, if I recall correctly, it was mentioned that, in the opinion of Soviet specialists, the quality of the French-made retroreflectors was several times higher than that of their American counterparts. I think that's important, because our Lunokhods were launched after the Americans had already begun their moonshots, and we'll analyze that later.
Actually, it's a complex issue. On one hand, the French triple prisms with silver metallization had a reflection coefficient 3 times higher than the American ones. They also had a larger aperture. The edge of the triangular prism was just over 10 centimeters. True, the active part was only about 2/3 of the triangular opening, but still, the effective aperture was around 6 point something centimeters. That's roughly twice the size of the American reflectors, which had an aperture of 38 millimeters. This aperture is very important for the intensity of the reflected signal, since the divergence of the reflected beam is determined precisely by the aperture of the retroreflector elements. So, the larger French prisms produce tighter, more intense beams than the small American ones. However, the Americans had their own reasons for choosing that design. There's a scientific paper where they explain why they opted for that particular technical solution, using small prisms, but many of them. The Apollo 11 and Apollo 14 arrays each have 100 small prisms, while Apollo 15 carries an array of 300 prisms.
I believe your presentation includes photographs of those platforms.
Here they are. The Apollo 11 and Apollo 14 reflectors look similar, each containing 100 small prisms, while Apollo 15's, though the photo is a bit tilted, has 300, 3 times as many. But the prisms themselves are identical. These panels with retroreflectors were mounted on the front of the Lunokhods at a slight forward angle. I'll explain later why that was done. Next is a photograph by Mark Robinson from the School of Earth and Space Exploration at the University of Arizona. This is Lunokhod 2. You can notice it has 3 cameras instead of 2. But the retroreflector is mounted the same way, at the front, tilted straight forward. The image shows the location of the Luna 21 lander, and a white cross marks where the Lunokhod itself sits in the Bay of Le Monnier, on the southern edge of the crater. What are retroreflectors for? First of all, they produce a signal that is very compact in time. Not only do all photons entering a retroreflector come back in the direction they came from, but they all exit simultaneously, regardless of where on the reflector they entered. That's an interesting mathematical fact. Just as they entered together, they leave together. The retroreflector panels on Apollo 11 and Apollo 14 were designed so that the reflected signal would be 1 or 2 orders of magnitude stronger than what would theoretically be possible from lunar soil alone. This is from the paper by Fowler and Wampler, The Lunar Laser Reflector, published in Scientific American in 1970.
So, what you've just told us are the theoretical principles behind the technical designs of around 1970.
Exactly, actually, even the late 1960s. The reasoning goes like this. Why a compact beam can't come from the lunar surface? If a laser beam hits the surface at an angle, the photons obviously reflect from wherever they strike the regolith, scattering in all directions. Given that the beam diameter is fairly large, and the length of the reflected ellipse is proportional to the cotangent of the deviation angle from the sub-Earth point. At noticeable angles, this distance can reach hundreds or even thousands of kilometers. Naturally, the signal gets spread out and can't produce a sharp peak on the histogram. But that assumes the moon is smooth, like a billiard ball, without ravines, mountains, or craters. Therefore, the claim that the lunar surface cannot produce a compact signal isn't really sound. Next, when discussing where a detected photon might have come from, we must always consider 3 hypotheses. First, reflection from the lunar surface itself, because the moon does reflect photons. Its albedo is low, around 7 to 8%, meaning the moon is actually quite dark. Still, it reflects something. At night we see sunlight reflected from it. So, if the moon reflects photons from the sun, it can just as well reflect photons from a laser. The second hypothesis is reflection from a retroreflector. And the third is various electronic noise or background illumination, since some photons can scatter in the atmosphere and be mistakenly picked up by the telescope. In such systems, there's always a certain level of noise. Therefore, when we detect 1, 2, or 3 photons, we have to approach the issue very carefully and not immediately shout, "Hooray, it's a reflection from the retroreflector." We must consider all three hypotheses, weigh them somehow, and reject some, based on certain criteria. In other words, we need to analyze it properly. This is Apollo 11 preliminary science report.
It was published by the Americans themselves.
It was published by the Americans themselves, specifically by NASA. So, in terms of status, it's not exactly a peer-reviewed scientific journal. It's an internal NASA publication. But it does describe that the measured range time could have three possible sources: a return from the retroreflector, a return from the lunar surface, or random noise coincidence from reflected sunlight and background illumination. Statistically, in a series of 1,200 firings, 35 to 50 noise coincidences and about 30 lunar surface ranges are expected. Because the numbers agree, within acceptable limits, with the total number measured, it is not obvious that returns from retroreflectors were measured. Because there was no observed signal increase by a factor of 10 to 100, as Fowler and Wampler had predicted, well-founded doubts were already expressed in that report. On the contrary, the level of the reflected signal corresponds to what would be expected from the lunar surface. Therefore, we cannot say that the reflections came specifically from the retroreflector.
A firing means a single laser pulse?
Yes, a laser pulse. They call it a firing, and I use that term too. So, already back in 1969, immediately after the Apollo 11 mission, experiments were conducted, and it was noted that the signal level was insufficient. And even now, the situation hasn't improved much, despite the highly advanced equipment at the Apache Point Observatory. They have excellent hardware, but the experimental results still don't match the theoretical calculations. According to those calculations, the references are provided. When targeting the Apollo 11 or Apollo 14 retroreflectors from Apache Point, about 5 photons per firing should be detected on average, and about 15 per firing from Apollo 15.
And how many are actually detected?
In practice, only 2 photons are registered from 5 firings.
5 per firing expected, but 2 from 5 firings observed.
Exactly, a difference of 36 times. So, it's unconvincing that this is the retroreflector at work. It doesn't shine in accordance with the theoretical prediction.